Our last trick here is what's called Descartes' rule of signs. You'll notice here that I call this Descartes' rule of signs, whereas a lot of resources would just call it Descartes' rule of signs, drop that extra S there. But as important as Descartes is, and as much as his head should be swelled for all the work that he did in this class's material, he's not Jesus, and the rule is you only do that if it's Jesus. So I say Descartes'. But anyway, what this gives us is a way to characterize the number of real zeros that we can have for a polynomial function. If we want to describe the positive real zeros, then either the number of positive real zeros is going to be equal to the number of sign changes for our function, or an even number less than the number of sign changes, where if you have exactly one sign change, then you're going to have exactly one positive real zero. Meanwhile, the number of negative real zeros is either going to be the number of sign changes for f of negative x, that flipped version, or it's an even number less than f of negative x. And yeah, these are a lot of stages, a lot of pieces. It might not seem very clear at all what this does, but let's just take it quickly here to think about the one that we started with, that x to the fifth minus x minus 1, because that changes sign once, going from positive at x to the fifth to negative at x, and staying there, it has exactly one positive real root. And if we flip the signs for this, we'll see that it has none for that reason, where actually this does have exactly one positive root. It has exactly one root overall, which is not a nice number. Not at all. So let's finish here with one more example that maybe has more potential. So for this, we want to determine the number of positive and negative real zeros of the function f of x equals x to the fourth minus 12x cubed plus 81x squared minus 37x plus 110. So what we have to do here is look at that function and recognize that going from x to the fourth to negative 12x cubed is one sign change. Going to 81x squared is another sign change. Going to negative 37x is another sign change. And going to positive 110 is a fourth sign change. So from Descartes' rule of signs, because this changes signs 4 times, f of x changes 4 times, that means we have either 4 positive real roots, or 2, or 0 positive real roots. Meanwhile, for the other case, if we want f of negative x, we need to actually get f of negative x. So we're going to plug in a negative x for that function, and what we will end up with is negative x to the fourth plus negative x cubed times negative 12 plus 81 negative x squared minus 37 times negative x plus 110, which actually ends up resolving all of the sign changes. So we have none sign changes. So we have none real roots. That is because f of negative x does not change signs. That sings. Signs, excuse me. Not SIGs either, signs. Jeez. We have no negative real roots. Where what you can think of Descartes' rule of signs as working off of is the idea that when you have a change of sign, it's almost like a curve in the function. And when the function curves, it's either going to reach the axis or it will curve back first because of another change in sign. So you have to have that either these things cancel each other out in time, or they don't. You cross the axis, then come back and cross the axis again. It's a little bit loose, but it should give some intuition for how this thing works. It's actually a pretty advanced little piece of logic, a bit beyond us to talk about it in detail. But anyway, that's our last little characterization. We can use our little trick here for getting the zeros of polynomials. We've talked a lot about dividing polynomials to get other polynomials. So next what we're going to do is talk about dividing polynomials and what that looks like itself as a function, which means we're going to be looking at what are called rational functions.